So, we will start with discussing the mixing of the entropy change for mixing of two ideal gases. Okay. So, we will discuss entropy change for mixing of two ideal gases. Okay. So, suppose initially we have a system having two containers, and in one container bromine gas is there, in another container nitrogen gas is there. So, this is our initial state. And there is a stopcock between them. If we remove the stopcock, and they will mix, right. So, here we have bromine plus nitrogen, here also we have bromine plus nitrogen, and this is our final state. We are assuming here that both bromine and nitrogen, they behave ideally. Okay. And our goal is to calculate the entropy of mixing. Our goal is to calculate the entropy of mixing of bromine and nitrogen. So, what is entropy change for nitrogen gas molecule? So, N N2 R ln because we know delta S is nothing but N R ln V final by V initial. We already discussed that. Okay. Here V N2 is the volume of this container, and V Br2 is the volume of this container. Okay. And N N2 here, N N2 is the number of moles of N2 gas. So, this is the entropy change for nitrogen gas. What about entropy change for bromine gas? We say this is delta Sbr2. In similar manner, we can write right. So, what is the total entropy change? That is nothing but entropy change for mixing. So, delta S mix is nothing but delta S N2 plus delta S Br2, right. So, we can write this one is like N N2 R ln V N2 plus V B at 2 by V N2 plus N B at 2 R ln V N2 plus V B at 2 by V B at 2, right. Very simple. Next, we can write like minus N N2 R ln V N2 by minus N B at 2 R right. Now, at constant temperature and pressure, for ideal gas, volume is proportional to number of moles, right. Okay. So, we can write delta S mix right. Now, we will just do some manipulation here. Where N is nothing but of N N2 plus N B at 2, or total number of moles in the system. So, we can write delta S mix where x N2 is mole fraction of N2, right. And this is nothing but your number of moles of N2 by total number of moles. Okay. And x B at 2, similarly, x B at 2 is the mole fraction of B at 2, and this is nothing but number of moles of B at 2 by total number of moles. Okay. So, we can simplify this expression, or in general we can write, delta S mixing is minus N R sum over I x I ln x I, right, where x I is the mole fraction of ith species. Okay. And in general is a fraction. Okay, so xi, value of xi is, or value of xi falls in between zero and 1, right. Okay. So, basically xi is a fractional quantity, is fraction, right. So, delta is mixing is greater than 0. Okay. So, it says that entropy of mixing or mixing of entropy of mixing is positive, and say entropy of mixing is positive. Okay, or in other words, okay, the mixing process is entropically favorable. Next, we discuss the entropy change arising from a phase transition. So, next we will discuss what is the entropy change due to phase transition. Okay. Now, all phase transitions, suppose you have solid ice, when it melts, it gives liquid water, and from there we get water vapor, right. So, from solid to liquid, liquid to vapor, right. So, when phase transition takes place, so these phase transitions are accompanied by change of entropy, okay, because in case of solid ice, okay, so the system is not that much chaotic, but when it melts and forms liquid water, molecules are more chaotic. When it further boils, gives water vapor, is further more chaotic water molecules are. Okay. So, under the condition of constant pressure, the latent heat of a phase transition is nothing but its enthalpy of transition, and we call it delta H trans. Delta H transition. Okay. At the temperature of transition, if we say that transition temperature is T trans, okay, the system is in equilibrium, right. So, the heat is transferred reversibly from the surroundings, right. Okay. So, heat is transferred reversibly from the process, because this is an equilibrium process. Okay. Okay. So, we can write the entropy of transition if we say delta S transition is nothing but delta H transition by T transition, right. Now, we will move, okay, we will move to something else. Okay. So far what we discussed? We discussed that, or we know ds system is greater than 0 for spontaneous process, right. But this is applicable for isolated system only. So, ds system, the change in entropy for the system greater than 0 for, it says that okay, the process is spontaneous process, but this condition is applicable only for isolated system. Okay. But in general means process can be system can be isolated or non isolated. In general, ds total is nothing but ds universe equals to ds system plus ds surroundings is to be greater than 0 for spontaneous process. So, in order to judge whether a system is a spontaneous or a non-spontaneous process, we need to calculate two different quantities, right. One is ds system, another is ds surroundings. We will then sum them up and then we will calculate ds total or ds universe, and then we will check whether the value of this quantity is greater than 0 or not. Then we can say that process is spontaneous or not. Okay. So, in general, we need to calculate two quantities, ds system and ds surroundings, to judge or to examine whether the process is so we need to calculate two different quantities, ds system and ds surroundings, okay, in order to judge whether the process is a spontaneous or not. It would be better if we can identify the spontaneity of any process by calculating only one parameter, right. So, it would be better if we can identify the spontaneity of any process by calculating only one parameter, right. by calculating only one parameter, right. And it would have been further better if the parameter is a state function, right. Okay. So, let us see whether we can have one single parameter that can tell us whether the process is spontaneous or not. Okay. So, from first law of thermodynamics we know dU is del Q plus del W, right. At constant volume, when volume is constant, at constant volume means no PV work, right. When volume is constant, there is no PV work. So, dU is del Q, right. And in this special case, when del W is 0, du we can write dq, and q is a state function in this special case when del W is 0. Okay. Now, in previous class we discussed about Clausius inequality, and we know ds is greater than equal to del q by t. Okay. So, it says T ds is greater than equal to del q. So, we can write du is less than equal to T ds, okay. Or we can write du minus T ds less than equal to 0 at constant volume. Okay. So, you can further write du minus Ts less than equal to 0 at constant volume and temperature. Okay. And this u minus Ts is known as Helmholtz free energy A. Okay. So, A at constant temperature and volume less than equal to 0. Okay. So, if you go back and check it, we use classical Clausius inequality, right, here. So, this is the Clausius inequality we have used here. Okay. So, if you correlate with that and this expression, we can say this negative sign represents spontaneous process. And equal sign represents equilibrium. And A here we defined as u minus Ts. So, A is known as A is known as Helmholtz free energy or sometimes Helmholtz free energy. Okay. So, this is the condition, this equation, if we say equation 1, this is the condition to check a process is spontaneous or not when the process is being carried out at constant temperature and at constant volume. And this A is a state function. We can prove it. So, if we like we plotted for entropy, if we plot a schematic diagram where we are plotting in Helmholtz energy change versus time, we get like this. So, here dA at constant temperature volume is less than 0 and dA dV equals to 0. Here this is equilibrium and this is spontaneous process. And this is known as a minimum. Okay, so, a process when dA at constant temperature and volume is greater than 0 cannot be a spontaneous one unless and until we do some work, okay, and make the process spontaneous one. Okay. So, we got A is u minus Ts, or we can write del A equals to del u minus T del S at constant T. Okay. And V, suppose. Okay. Now, if we look at this equation, equation 2 here, when delta U is less than 0 and delta S is positive, when delta U is negative and delta S is positive, this makes delta A constant T V less than 0. So, it makes the process a spontaneous one. Okay. But if delta U and delta S, they have different sign. Okay. Suppose delta U is less than 0 and delta S is also less than 0. If they possess the same sign, okay, in that case we need to examine the value of delta U and T delta S, okay, and then only we can judge whether the process is a spontaneous one or not. Okay. So, when delta U is negative and delta S is also negative, okay, we need to consider both the quantities. When delta, suppose if delta U is positive, if delta U is positive and delta S is also positive, then also we need to examine both delta U and T delta S terms. Okay. Both the terms we need to consider, and then only we can judge whether the process is spontaneous or what, spontaneous one or not. Okay. Now, if we think about the entropy of mixing, the experiment we carried out for the mixing of bromine and nitrogen gas that we discussed just now, we know delta S mixing is minus Nr sum over I xi ln xi, right? And this mixing process, for this mixing process delta U is 0, right. So, what is delta A there? So, delta A mix is nothing but N R T sum over I xi ln xi. And since xi is fraction, since mole fraction is a fractional quantity, we can say delta A mix is less than 0. Okay. So, we now discuss the concept of Helmholtz free energy, but there is a drawback there, because the most of the chemical reactions are being carried out or are carried out at constant temperature and pressure. So, we need to have a parameter or rather a state function. By examining that state function at constant temperature and pressure process, if we can say the process is spontaneous one or not, right. So, that is how the Gibbs free energy or Gibbs energy term has been coined. Okay. So, Gibbs free energy, the concept of Gibbs free energy or free energy term comes. So, Gibbs free energy, sometimes we call Gibbs energy, is termed as G. And why we need to have G, why Helmholtz free energy is not sufficient? Because most of the, or since most of the reactions occur at constant T and P. So, it would be better if we define a state function which helps in determining the spontaneity of a process at constant temperature and pressure. Okay. So, we will define that quantity now. So, we know dEu is del Q plus del W. Remember, here pressure is constant, unlike for the case of Helmholtz free energy where volume was constant. So, we could able to make del W 0, but here del W is not 0. Okay. So, and now we know again del Q by T or ds is greater than equal to del Q by T. Okay. Or in other words, T ds is greater than or equal to del Q. So, we write dEu so, since del W is not 0 here, so del W is nothing but P dV. Okay. So, we can write d So, at constant temperature and pressure, this is explained. And we know U plus PV is nothing but enthalpy. Okay. So, we can write dH minus Ts less than equal to 0, or we can write dG at constant temperature and pressure less than equal to 0. Okay. So, this is the expression del dG at constant temperature pressure less than equals to 0 is the conditions for spontaneity of a process. So, here G, so G here is nothing but H minus Ts. Okay. Next, we will discuss how G varies with temperature and pressure. So, variation of Gibbs free energy with temperature and pressure. So, this thing we will discuss now. This is very important expression will arrive, two very important expression will arrive. Okay. If we consider the variation of Gibbs free energy with temperature and pressure. Okay, so we know G is nothing but H minus Ts. So we can write dG is dH minus TdS minus SdT. Now H is U plus PV. So dH is nothing but du plus PdV plus VdP, right. So if you substitute the value of dH here, we get dG is du plus PdV plus VdP minus TdS minus SdT. Next is what is du plus PdV? So du plus PdV, this term is nothing but dq, and TdS also is nothing but dq. Okay. So we write dG is nothing but dq plus VdP minus TdS minus SdT. Okay. And this TdS also is nothing but dq, or rather del q here. We cannot write dq here, we write del q. Okay. So we write dG is VdP minus SdT. So this is a very, very important expression. Okay. Why? We will see now. Okay. So we get dG equals to VdP minus SdT. From there we can write del G by del P at constant temperature gives volume. Okay. So if we vary G with pressure at constant temperature, we get volume. So this is our equation, suppose this is our equation 2 here, and del G by del T at constant pressure, we write minus S. So this is our equation 3. And these two expressions are very, very important. We need to remember those two expressions. Okay. Now if we consider, first we will consider this expression, expression 3. Okay. So we will consider expression 3 here. Okay. So we get, this is the expression 3. Okay. Now if we plot G versus temperature in Kelvin, right. Expression 3 says variation of Gibbs free energy with temperature at constant pressure. So this is at constant pressure. Okay. So in expression 3, if we look at expression 3 here, we get that the slope of the curve is negative, right, because absolute entropy is a positive quantity. So the slope of G versus T plot will be having negative slope. So the plot of G versus T will be having negative slope. So we get like this. If you look at the figure carefully, what do you observe? You observe that the slope is different up to this point. Okay. Again from this point to this point, after this point the slope is also different here. Okay. So this is known as melting temperature. Okay, melting point we can say. So this is melting point. This point is melting point, and this is boiling point. Why the slopes are different here? So the slopes are different here because S gas, absolute entropy for gas molecule is much higher than S liquid, which is greater than S solid. Okay. That is why we get different slopes here. So, this region is our solid region, this is liquid region and this is gas region. Okay. Okay, so, this is at constant pressure. Okay. When pressure is constant, we get this kind of plot. If we plot G versus T. Now, few important expressions, now we will consider another expression, right, that expression 2. So, from expression 2 or equation 2, we can write dg equals to v dp, okay, and g1 to g2 limits are here and here p1 to p2. Okay. So, for ideal gas, okay, V is nothing but nRT by P. So, we can write del G is nothing but G2 minus G1 is nRT ln P2 by P1. Okay. Or we can further write del G is nothing but nRT ln V1 by V2, since P is inversely proportional to V at constant T and N. Okay. So, we get another good expression, another nice expression for calculating delta G here. Okay. So far what we got, if we summarize what we have discussed so far, we have du is TdS, or rather we can write in del Q, if the process is reversible one, del Q plus del W reversible. Okay. So, we can write du is del Q plus del W, and we can write this one as TdS minus PdV. Okay. And from here we can write del U by del S at constant volume is T, and del U by del V at constant S is minus P. Okay. So, from here we get the definition of absolute entropy, absolute temperature. Okay. If we calculate del U by del S at constant V, we get temperature. Now, we also got dH. dH is nothing but du plus PdV plus VdP, right. Okay. So, du plus PdV is nothing but del Q plus VdP, and del Q is nothing but TdS plus VdP. Okay. So, if we do the way we did it before, we get del H by del S at constant pressure is T, and del H by del P at constant S is V. Okay. Then we have A. So, we know A. So, dA is du minus TdS minus SdT, right. So, if we further simplify this one, you get du is minus PdV minus SdT. Okay. Because this du you can further write like TdS minus PdV minus TdS minus SdT. This is your del Q and this is your del W. Okay. So, from this expression dA equals to minus PdV minus SdT, we can write del A by del V at constant temperature is minus P and del A by del T at constant V is minus S. And lastly, we know dG is dH minus SdT minus T ds, right? And H we know du plus PdV plus VdP minus SdT minus TdS, and the whole term is nothing but del Q, okay? And this is also del Q. So, we get dG is VdP minus TdS. Okay. So, we can write del G by del P at constant temperature gives volume and del G by del S at constant pressure, oops, not TdS, this is SdT. Oops, sorry, this is SdT. So, this is not del Q, the other one is del Q. Here, this is del Q. So, we get del G by del T at constant pressure is minus S. Okay. So, we have obtained so far 8 important expressions. Okay. So, from these expressions we can derive Maxwell's relationships. So, thank you very much.